Right now, at the exact same moment, one end of this planet is doing something it has never done before in recorded history, while the other end is doing the complete opposite. In March of this year, the Arctic Ocean grew less winter sea ice than it has ever grown in the entire history of satellite measurement. At the very same time, just days apart, a research station in Antarctica recorded the coldest temperature ever measured anywhere on Earth. Read that back, because it sounds like a contradiction, and honestly, at first glance, it is one. One pole is running out of ice, the other pole just set an all-time cold record. Same planet, same week. Completely opposite behavior. And when climate scientists sat down to actually explain what was happening, they realized this was not two unrelated stories playing out in different corners of the globe. It was one connected system, showing signs of instability at both ends simultaneously. And what they found underneath both of these events is genuinely more unsettling than either headline on its own. Stick with me, because by the end of this video, you are going to understand exactly why researchers keep describing this as a warning sign rather than just an unusual season. If you have ever wondered why the poles seem to make headlines every single year with numbers that sound more extreme than the last, drop a comment and let me know which one worries you more, the Arctic or Antarctica, because I want to hear your take once we get through everything today. And if you want to keep up with exactly what is happening at the extreme edges of this planet as it develops, subscribe now, because this is a story we are going to keep coming back to. Let's break down exactly what happened, because the sequence and the timing here is what actually makes this remarkable. Start with the Arctic, because the Arctic story this year is really a story about absence. Every single year, without fail, the Arctic Ocean freezes over during the long, dark winter and then melts back during the short summer. That is the basic rhythm this region has followed for as long as humans have been able to measure it. Scientists track this cycle by watching for what is called the winter maximum, the single day each year when Arctic sea ice reaches its largest extent before the seasonal melt begins. This year, that peak came in at 52 million square miles of ice. And that number might sound big until you compare it to where it should be. It was about 525,000 square miles below the 1981 to 2010 average for that same point in the year. Just to put that gap in perspective, 525,000 square miles is roughly twice the size of the entire state of Texas. That is not a sliver of missing ice around the edges. That is an area larger than most countries on Earth simply failing to freeze this year. And this wasn't a one-year blip either. It was statistically tied with the previous year's winter maximum for the lowest ever recorded, meaning the Arctic has now posted back-to-back winters where it could not build back the ice it used to reliably grow every single year. Here's why that particular number matters so much to researchers who study this for a living. Sea ice does not just sit there being cold and white. It performs an active job for the entire planet, acting like a reflective shield that bounces a huge percentage of incoming sunlight straight back out into space before it ever has the chance to warm the ocean underneath. Scientists call this the albedo effect, and it works almost like a mirror sitting on top of the water. When that mirror shrinks, more of the ocean surface is left exposed, and dark, open ocean water does something ice never does. It absorbs sunlight instead of reflecting it, and that absorbed heat then gets released back into the atmosphere, especially in the following autumn and winter, making it even harder for ice to reform the next time the cold season arrives. Researchers actually have a phrase for this feedback loop, calling it a genuine global warming signal rather than just noisy year-to-year weather. Because the mechanism behind it is directly tied to how much heat the planet as a whole is holding on to. In this particular winter, the shrinking happened while temperatures were breaking records almost everywhere else on the planet at the exact same time, across the United States, throughout Mexico and Australia, across northern Africa, and through large parts of northern Europe. One climatologist who has spent years tracking extreme temperature records called that specific stretch of March some of the most extreme heat ever documented on a global scale. So the Arctic wasn't failing to freeze in isolation. It was failing to freeze while the rest of the planet was simultaneously baking. Now here is where the story takes a genuinely strange turn. Because while all of that was happening in the far north, something almost impossible to reconcile was unfolding at the exact opposite end of the Earth. In that very same week in March, a research station deep in Antarctica recorded a temperature of minus 105, 5 degrees Fahrenheit, which converts to minus 76, 4 degrees Celsius. That is not just a cold reading. According to the meteorologists who track and verify extreme weather records globally, that is officially the coldest temperature recorded anywhere on the planet during that entire month. And it stands among the most extreme cold readings ever documented on Earth in general. So think about what actually happened here. In the same 7-day stretch, one pole logged its worst failure to freeze in the history of modern measurement, while the other pole plunged to depths of cold that pushed the boundaries of what meteorologists have ever recorded anywhere on this planet. If you only read one of those headlines, you would draw a completely different conclusion about the state of the planet than if you only read the other one. That is exactly the trap researchers are trying to help people avoid. And it is exactly why understanding both halves of this story together matters so much. So how can both of these things be true simultaneously without contradicting each other? This is where we actually need to understand that the Arctic and Antarctica are not mirror images of each other, even though we tend to lump them together in our heads as basically the same kind of place, just opposite ends of a globe. They are fundamentally different systems, built on fundamentally different geography. And that difference is the entire key to this puzzle. The Arctic is essentially an ocean, a body of seawater, sitting almost fully enclosed by the surrounding land masses of North America, Europe, and Asia. Antarctica, on the other hand, is the reverse. It is a genuine continent, an enormous landmass roughly 1.5 times the size of the United States, sitting isolated at the bottom of the world and completely surrounded by the open waters of the Southern Ocean. That single structural difference changes everything about how each pole responds to a warming planet. Because the Arctic is mostly ocean, it is directly exposed to warming sea currents and to that dark water absorption feedback loop we just touched through, which is why it tends to respond to global warming relatively quickly and relatively directly. Antarctica, sitting on solid ground at a massive elevation, surrounded by a ring of powerful, isolating ocean currents and high-altitude winds, has historically been far more insulated from the same warming trend, at least across the interior of the continent. But insulated does not mean unaffected, and this is exactly where scientists have discovered that Antarctica is capable of its own wild extremes, just pointed in the opposite direction from what happened at the Arctic this year. Researchers went back and studied a genuinely bizarre event that had happened a couple of years earlier in the middle of the Antarctic winter during the months of total darkness when temperatures typically sit below minus 30 degrees Celsius. Instead, parts of East Antarctica warmed by up to 28 degrees Celsius above their seasonal average, and that extreme heat did not just spike for a day and vanish, it held on for more than 2 weeks straight in the dead of the polar night. To understand how genuinely strange that is, researchers offered a direct comparison, explaining that an anomaly of that scale happening in a place like the United Kingdom would be the equivalent of January temperatures suddenly jumping into the mid-30s Celsius, in the middle of what should be winter. When the scientific team studying that event published their full analysis this year, they concluded it was not just an unusual patch of weather. It was described as a rare atmospheric disturbance, one that had been directly amplified by human-caused climate change, driven by a combination of a weakened polar vortex, a surge of warm, moist air known as an atmospheric river slamming into the continent, and record low sea ice conditions that had already left the surrounding ocean more exposed to atmospheric heat than usual. In other words, the same continent that just posted one of the coldest temperatures ever recorded on the planet has, within recent memory, also produced one of the most extreme and sustained winter heat anomalies ever documented anywhere on Earth. Antarctica is not a passive, frozen constant sitting quietly at the bottom of the map. It is capable of violent swings in both directions, and researchers are increasingly convinced that instability itself, rather than a single steady trend, is becoming the actual signature of what is happening at the poles. It also helps to understand exactly what a polar vortex actually is, because that term gets thrown around constantly in weather coverage without much explanation. The polar vortex is a massive, swirling pocket of extremely cold air that sits high in the atmosphere above both poles, held in place through the winter by a ring of strong, fast-moving winds circling around it like a wall. When that wall of wind stays strong and stable, it effectively locks the coldest air in place near the pole, keeping it contained. But when that wall weakens, either from a sudden warming event higher in the atmosphere or from disruptions caused by shifting temperature patterns below it, the vortex can wobble, stretch, or even split apart entirely, allowing pockets of that extreme cold air to spill out toward the mid-latitudes, while warmer air rushes in to fill the space left behind at the pole. This is exactly the mechanism researchers pointed to when explaining that prolonged Antarctic winter heat wave, a weakened vortex allowing an atmospheric river of warm, moist ocean air to punch directly into the interior of the continent during a season when that air mass should have had no way of getting anywhere near there. And it is the same basic mechanism, just running in reverse, that has been blamed for some of the brutal cold snaps that have hit places like Texas and the American Midwest in recent winters, moments when a wobbling Arctic vortex sends genuinely polar air thousands of miles south into regions that are utterly unprepared for it. So when scientists talk about the poles becoming more unstable, this vortex behavior is a huge part of what they mean. It is not simply that the poles themselves are getting warmer or colder in isolation. It is that the entire system holding cold air in place at the top and bottom of the planet is becoming less reliable at doing its job, and the spillover effects show up as extreme weather thousands of miles away from either pole. There is another piece of this puzzle that deserves attention because it connects directly to something a lot of people have heard about in passing without fully understanding why scientists worry about it so much, and that is the risk of slowing ocean currents. The Atlantic Ocean has a massive circulation system running through it, carrying warm water up from the tropics toward the North Atlantic, where it cools, sinks, and flows back southward at depth, acting essentially like a giant conveyor belt that helps regulate temperatures across an enormous stretch of the planet, including much of Europe. That entire system depends heavily on cold, dense, salty water sinking in the North Atlantic to keep the circulation moving. As Arctic ice melts and dumps enormous volumes of fresh water into that same region, it dilutes the salinity of the surface water, making it lighter and less prone to sinking, which several research teams now believe is measurably slowing that circulation down. A slower version of that system would not just mean colder winters in parts of Europe, counterintuitive as that sounds for a warming planet, it would also mean disrupted rainfall patterns across large parts of the tropics, changes to fish populations that entire coastal economies depend on, and further destabilization of the very temperature gradients that keep the jet stream behaving predictably in the first place. None of this is happening in some far-off future scenario disconnected from the events we just walked through. It is directly downstream of the same shrinking Arctic ice that produced this year's record low winter maximum, which is exactly why researchers treat that one number, 525,000 square miles below average, as something far more significant than a single unusual season. This is genuinely important to sit with for a moment because it directly challenges the mental shortcut a lot of people use when they think about the poles. The assumption tends to go something like this. If the Arctic is melting, then the whole planet must be warming uniformly. And if Antarctica sets a cold record, that must mean the warming trend is somehow reversing or being exaggerated. Neither one of those conclusions is actually correct, and scientists have been explicit about this exact confusion for years. Antarctic sea ice, unlike the Arctic, is heavily influenced by localized weather patterns and shifting ocean currents circling the continent, which means it can genuinely diverge from the broader global trend for extended stretches of time without that divergence, meaning the underlying warming has stopped. In fact, researchers tracking the numbers noted that even though Antarctica's own summer sea ice low point earlier this year came in below its 30-year average, it was nowhere near the record lows the continent had posted in the several years just before that. So even within Antarctica's own recent history, you can find years of sudden, dramatic melting followed by years of relative, if still below average, recovery. This is exactly the kind of noisy, volatile pattern that makes single data points dangerous to interpret in isolation. And it is exactly why serious researchers spend so much energy trying to explain the full picture instead of just reacting to whichever headline broke that week. Now, if all of this only affected penguins and polar bears, most of us watching this could reasonably shrug it off as a distant, if fascinating problem, happening somewhere far away. But that is simply not how these two systems work, and this is the part of the story that connects everything we've just walked through to your own life, wherever you happen to be watching this from. What happens at the poles does not stay at the poles. One retired American admiral who has spent years studying this exact issue put it about as plainly as it can be put, saying directly that what happens in the Arctic does not stay in the Arctic. And the mechanism behind that statement is worth actually understanding, rather than just accepting on faith. As Arctic sea ice continues shrinking and exposing more dark ocean water, that absorbed heat does not just sit quietly in the Arctic Ocean. It gets transferred into the atmosphere and it directly interferes with something called the jet stream, the powerful river of high-altitude wind that circles the northern hemisphere and largely dictates where storms track, how long heat waves linger in one place, and how cold air masses move around the globe during winter. A warming Arctic reduces the temperature difference between the pole and the equator, and that shrinking temperature gradient is exactly what powers the jet stream in the first place. Weaken that gradient, and the jet stream itself tends to weaken and become far more wavy and erratic, which is part of the reason we have seen such a dramatic rise in prolonged heat waves, unusually stalled storm systems, and extreme cold snaps hitting places that rarely used to experience them, all across the mid-latitudes where the vast majority of the human population actually lives. Meanwhile, on the Antarctic side of the planet, the concern runs in a different but equally serious direction, centered almost entirely on ice sitting on land rather than ice floating in the ocean. This distinction matters enormously because when sea ice melts, it does not meaningfully raise global sea levels, since it was already floating in the water to begin with, displacing roughly its own volume. But when land ice melts, whether that is the towering ice sheets covering Antarctica or the glaciers flowing off of it into the sea, that water is genuinely new water being added to the ocean, and it directly raises sea levels worldwide. And this is where some of the most alarming recent research comes in, because scientists studying Antarctica this year uncovered something that had been sitting hidden for a long time, quite literally beneath the surface. Researchers found long, previously undetected channels carved directly into the underside of Antarctica's floating ice shelves. Channels that appear capable of accelerating global sea level rise far faster than existing models had accounted for. These hidden channels essentially create pathways for warmer ocean water to reach further underneath the ice shelves than scientists had previously mapped, undermining the structural stability of the ice from below. In places nobody was watching closely because nobody knew those pathways were there. Alongside that discovery, satellite monitoring over the past couple of years has documented what researchers are calling the fastest Antarctic glacier retreat ever recorded, involving a glacier called Hectoria, which experienced a sudden collapse that saw it retreat by 8 full kilometers in a shockingly short window of time. Scientists studying that event found that Hectoria was sitting on a flat section of ice below sea level, a geometry that allowed enormous slabs of ice to break away and disintegrate far more rapidly than the slow, gradual retreat that had generally been assumed to be the normal pace for glaciers of this size. And then there is the glacier that has earned itself a nickname, specifically because of how much international concern it generates: Thwaites. Widely referred to by researchers and journalists alike as the Doomsday Glacier, scientists have spent years watching cracks spread across its eastern ice shelf because Thwaites alone holds enough ice to raise global sea levels by more than 2 feet if it were to fully collapse. And it also happens to be acting as a structural brace, holding back a much larger section of the West Antarctic ice sheet behind it. If Thwaites goes, it does not just contribute its own share of sea level rise, it potentially destabilizes everything sitting behind it too. That geometry is genuinely dangerous, because it means that once warm ocean water manages to work its way underneath the glacier's floating front and starts melting it from below, the retreat does not necessarily slow down as it moves inland. It can actually accelerate, since each new section the glacier retreats into sites in deeper water, exposing even more ice to direct contact with warm currents. Researchers have been documenting exactly this kind of ocean water intrusion underneath Thwaites for years now, using submarines, underwater robots, and radar surveys to map channels and cavities forming beneath the ice that simply were not visible from the surface. That is part of why the newly discovered channels running beneath other Antarctic ice shelves this year alarmed researchers so directly. It suggested that the kind of hidden accelerating vulnerability scientists had already been tracking underneath Thwaites, specifically, might be a far more widespread feature of Antarctica's ice shelves than anyone had previously mapped or accounted for in their models. To understand just how much is genuinely at stake here, it helps to zoom out to the full scale of what East Antarctica alone is holding in reserve. East Antarctica hosts the single largest ice sheet on the entire planet, and researchers have calculated that it contains enough frozen water to raise global sea levels by 52 meters. That is roughly 171 feet, if it were somehow to fully melt. Nobody studying this seriously believes that scenario is happening anytime soon, and it is important to be honest about that, rather than reaching for the most extreme possible framing just for effect. But scientists have spent decades genuinely puzzled by exactly how and why that ice sheet formed in the first place, and this year, researchers finally published new findings helping to solve part of that long-standing mystery, discovering that Antarctica actually became covered in ice around 34 million years ago, a full 25 million years before the Arctic region followed the same path and froze over itself. For a long time, falling atmospheric carbon dioxide levels were assumed to be the entire explanation for why the planet cooled during that ancient period, but researchers pointed out a problem with that theory. If dropping carbon dioxide alone were responsible, both poles should have cooled and frozen together at the same time. They didn't. Something else was clearly giving Antarctica a massive head start, and untangling exactly what that was is now helping researchers build far more accurate models of how these two poles are likely to respond differently as the planet continues warming today, rather than assuming they will behave identically just because they occupy similarly cold positions on the map. This is genuinely one of the most useful things to take away from all of this research, and it is worth pausing on directly because it cuts against how most of us naturally think about the two poles. We tend to mentally file the Arctic and Antarctica into the same basic category: cold, remote, icy, essentially interchangeable in our heads as symbols of a planet under stress. But scientists studying both regions closely are increasingly emphasizing that treating them as a matched pair is a mistake because it leads people to expect matching behavior and then get confused. Or worse, dismissive, the moment one pole does something that seems to contradict the other. When the Arctic posts a record low winter maximum and Antarctica simultaneously posts a record cold temperature, that is not the planet sending mixed signals. That is two structurally different systems, one an ocean, one a continent, each responding to the same underlying warming trend through their own distinct physical mechanisms, on their own distinct timelines. And the fact that they can look so different from each other in any given week is not evidence against a warming planet. It is evidence of exactly how complicated and regionally specific that warming actually is. So where does this actually leave us, sitting here, watching both of these headlines unfold in the same news cycle? The Arctic's shrinking winter ice and Antarctica's newly discovered hidden ice shelf channels and rapidly retreating glaciers are not two separate concerns happening to exist at the same time by coincidence. They are two expressions of the same broader story, a planet where the systems regulating our climate, our ocean currents, and our weather patterns are all showing measurable, accelerating signs of instability, even when that instability doesn't always look the same from one pole to the other, or even from one year to the next at the very same pole. Researchers who have spent time physically visiting both extremes have come away with a fairly consistent conclusion, describing a mounting frustration at how much impact these remote, seemingly disconnected regions actually have on the rest of the world, compared to how disconnected most people feel from them in daily life. The poles regulate global weather patterns. They regulate ocean currents that move heat around the entire planet. They even influence maritime food supplies that coastal communities everywhere depend on. And they are warming and destabilizing faster than almost anywhere else on Earth, with consequences that do not stay contained anywhere near either pole. If you found this genuinely useful for understanding a story that gets oversimplified constantly in headlines, hit like on this video right now, because it helps push this kind of careful breakdown in front of more people who are tired of getting one confusing, contradictory headline about the poles after another without any real explanation connecting them. And drop a comment telling me honestly, before watching this, did you assume the Arctic and Antarctica basically behave the same way? Or did you already know how differently these two systems actually work? I am genuinely curious how common that assumption still is. Here's the practical reality to hold on to as this story continues to develop in the months and years ahead. None of this means either pole is going to collapse overnight, and it would be dishonest to frame it that way, just to make the story feel more dramatic than the actual science supports. Thwaites is not going to fully disintegrate next year. East Antarctica's massive ice sheet is not going anywhere on any timescale that matters to any of us personally. But the trajectory that researchers are documenting, faster than expected glacier retreat, previously hidden channels, accelerating ice shelf instability, record low winter sea ice in the Arctic sitting right alongside genuinely extreme volatility in Antarctica, all of it points toward two systems that are behaving less and less like the stable, predictable regions they were assumed to be for most of modern scientific history. Scientists are not describing this as a single crisis event you need to brace for this year. They are describing it as an accelerating trend, one where the safe assumptions built on decades of relatively steady polar behavior are increasingly being proven wrong, one surprising data point at a time. Coastal communities, insurance markets, agricultural planners, and governments around the world are already beginning to plan around sea level projections and shifting weather patterns that are directly downstream of exactly what we've walked through today. Whether or not most people watching this have ever consciously connected those dots before. It also helps to know what scientists are actually watching for next, because this is not a story that simply ends with the data we already have. Researchers are closely tracking whether this year's Arctic winter maximum turns out to be a genuine outlier or the start of a new, lower baseline, something that will only become clear as more winters are added to the record in the coming years. On the Antarctic side, teams are continuing to monitor Hectoria and its neighboring glaciers for signs of whether that 8-kilometer retreat was an isolated event tied to its unusual below sea level geometry, or an early example of a collapse pattern that could show up elsewhere along similarly shaped sections of the coastline. Satellite missions, specifically designed to map ice thickness and detect exactly these kinds of hidden channels beneath ice shelves, are being expanded, precisely because this year's discoveries showed how much can apparently still be hiding in plain sight, underneath ice that has already been studied for decades. None of this research moves quickly, and none of it is designed to produce a dramatic single answer. It is slow, methodical, unglamorous work, largely carried out by small teams operating in some of the most physically punishing environments on the planet. And it is precisely that kind of patient monitoring that turned two seemingly unrelated headlines this year into a much more coherent and much more useful picture of what is actually happening at both ends of the Earth. The honest takeaway here is not panic, and it never has been, throughout any of the stories we cover on subjects like this. It is attention. Understanding that the Arctic and Antarctica are not simple interchangeable ice boxes sitting quietly at either end of the map, but genuinely different, genuinely complex systems, each capable of surprising even the scientists who study them for a living, is exactly the kind of understanding that helps you read the next headline about either pole with actual context instead of confusion. This year alone, we watched one pole fail to freeze the way it always has, and the other pole simultaneously plunged to one of the coldest readings ever recorded on the planet. And underneath both of those seemingly contradictory headlines set the same fundamental truth, that the systems holding the largest reserves of ice on Earth are shifting in ways researchers did not fully expect, on a timeline faster than most of the models built even just a few years ago predicted. That is exactly why scientists keep coming back to both ends of this planet, again and again, watching closely for whatever comes next. Subscribe if you want to stay with the story as new data comes in from both poles in the seasons ahead, because based on everything we just walked through, this is very unlikely to be the last surprising headline either region produces. Let me know in the comments which pole you think we should be watching more closely going forward, and I will see you in the next one.